Namaskar students. In this video, we will discuss proofs of some of the properties of beta and gamma function. In our previous video, we have discussed the definition of these two special functions, beta and gamma functions. We have discussed 7 or 8 properties of these beta and gamma function, done one problem also, which was based on gamma function. Now, in this video, we will be discussing or we will be proving some very important properties of beta and gamma function. So let us start with the relation. We will be establishing the relation here between beta and gamma function. We all know, we have discussed in our live sessions as well as in previous videos, the relation which we have between beta and gamma function. So if I write that relation, the relation between beta and gamma function is beta of m and n. This is equal to gamma of m, gamma of n, and this divided by gamma of m plus n. To prove this result, we will start with gamma of m. So let us start. We know gamma of m, this is given by this definite integral 0 to infinity e raised to power minus x raised to power m minus 1 dx. So what we have done, we have just written the definition of gamma function, that the gamma function is given by this definite integral. Now, for proving this result, for establishing this relation, we will be considering here substitution, assumption we will be making. We will be assuming that this x as t square. After this substitution, we will be finding the relation between dx and dt, and that relation will be this dx by dt will become 2t. So dx will be 2t dt. After having this substitution, this gamma m will be reduced to gamma m. There will be no change in the limits. The limits will be same, 0 to infinity. Let us convert it in terms of t. So e raised to power minus x will become e raised to power minus t square. X raised to power m minus 1, this term, it will become t this will become t raised to power 2 m minus 2, and this dx is 2t dt. If we further simplify it, we will get that gamma of m, this is equal to this integral. We are integrating it within the limits 0 to infinity, e raised to power minus t square. We can take this 2 outside, and t raised to power 2m minus 1 dt. If I change variable back to x, I can write it as gamma of m is equal to 2 times this integral 0 to infinity e raised to power minus x square x raised to power 2m minus 1 dx. So let us name this equation as equation 1. From this equation 1, let us write down an expression for gamma of n, because the result which we have to prove, it involves gamma n on the right hand side. So let us write down an expression for gamma n from this equation 1. We can write gamma n as 2. We are integrating from 0 to infinity e raised to power minus y square. Now we are using the variable y. Since we are finding now the gamma of n, so at the place of m, now we will be having n, 2n minus 1, and here we will be having dy. And let us name this equation as equation 2. The result which we have to prove involves the product of gamma m and gamma n. Right hand side, the numerator of the right hand side is gamma m, gamma n. So let us consider the product of these two, gamma m and gamma n. So we will get gamma m, gamma n. We have 2 in both of these, gamma m and gamma n, so it will become 4. And the limits on both the integrals are from 0 to infinity, 0 to infinity, 0 to infinity. If I combine the exponential term, it will be e raised to power minus is common, x square plus y square. We can see here we have e raised to power minus x square, e raised to power minus y square. So when we will be considering the product, it will be e whole raised to power minus x square plus y square, and x raised to power 2m minus 1, we have this one in that equation 1, x raised to power 2m minus 1, and in equation 2 we have y raised to power 2n minus 1, and we have here dx dy. So what is this on the right hand side? This is the double integral. I will explain you briefly about this double integral. So we can name this equation as equation 3. This is a double integral, and we will be solving this double integral by changing the variable from Cartesian coordinate system to polar coordinate system. So if I explain you briefly about the double integral, this is the notation for the double integral. We are integrating here the function f. F is the function of two variables x and y, and we are integrating it with respect to x and y over some two-dimensional region, say it be R. So when we evaluate the double integral, it is evaluated over some region. When we evaluate this one, definite integral, this f is function of one variable within some limits a to b, then it is evaluated over the interval AB on the real line. But when we are talking about the double integral, it is evaluated over some region, and that is two-dimensional region in plane. So when we evaluate double integral, we have some important things, important terms. The first one is region of integration. means what is R over which region we are integrating. The second thing which is important when we evaluate the double integral is the order of integration. And sometimes we change the variable, we follow change of variable technique for evaluating the double integrals. So here what we will be doing for evaluating the double integral which is present in third equation, we will be changing the variable. We will be assuming x as r cos theta and y as r sin theta. Means we are shifting from Cartesian coordinate system to polar coordinate system. So we will be using this change of variable. So we have this double integral. If I write down in the general way, let us assume that we are changing x to new set of variables, say u and v, with the help of some function, say g. And similarly, we have y in terms of u and v, and that function is, say, h. So we will be putting this x and we will be putting this y in this integrand f. On doing this, we will be having a new integrand, and that new integrand will be in the terms of these new variables u and v. So we are changing the variables from xy to uv. So when we change the variables, this double integral which I have written here, which is in xy, this becomes, we are changing the variable, we will be having some new integrand, say w, which will be obtained by putting here x and by putting here y. With the help of these equations, we will be using this g and h here, and we'll be getting new integrand, say w, and that will be in the terms of u and v. And this dx dy becomes modulus of this j. What is this j? J is called the Jacobian. And du dv, because now everything has been converted in u and v, so we will be integrating now with respect to u and v. This is called, j is called Jacobian. So we will be evaluating Jacobian with the help of these equations which we have for x and y, and we will be putting here this Jacobian, we will be finding the limits of u and v, and we will be evaluating this double integral which is on left hand side by converting it into new set of variables which are u and v. We are changing here the variables from xy to uv. But here, as I have mentioned, that we will be solving the double integral which is present in equation third by changing it into the polar coordinates. So what are the polar coordinates? You all are aware about it. We know x is equal to r cos theta and y is equal to r sin theta. If I show you here, we are considering here the plane, Cartesian plane. This is our y-axis, this is our x-axis, and say this is any point whose coordinates are, say, x and y. So what is the significance of this r and theta? R is this distance and theta is the angle with a positive direction of x-axis. So if you will find x and y from this, with the help of trigonometric identities results, you can easily check here that x will be r cos theta and y will be r sin theta. So here we have written that x is in terms of uv, y is in terms of uv, but here we are changing to polar coordinates which are r and theta. So x is r cos theta, means here g is actually r cos theta. What is the definition of x? X is r cos theta. And what is y? Y is r sin theta. Why we are using this polar coordinate system? Because with the help of polar coordinate system, with the help of these new set of variables r and theta, we can easily evaluate the integral which is present in this equation third. With this, what will be our Jacobian? Because we need Jacobian also. Earlier, I have not mentioned that how we find out the Jacobian. this Jacobian, the notation, another notation for the Jacobian is we are finding the Jacobian of xy with respect to r and theta. This is another notation for the Jacobian. How we read it? We are finding here the Jacobian of xy with respect to r and theta. This Jacobian is given by this determinant. This is del x by del r. Again, this is new for you. Del x by del r, this is the notation of partial derivative. We are not using here d. We are not using here the notation of ordinary derivative. We are using here the notation of partial derivative del x by del r. Then we will be having partial derivative of x with respect to theta. We read it as del x by del theta. Now we have y here. So second row will be for y, partial derivatives of y. So it will be partial derivative of y with respect to r and partial derivative of y with respect to theta. So we have this one. How we evaluate partial derivatives and when we use this notation of partial derivative, let me tell you this thing. Partial derivatives, we talk when we talk about the function of more than one variable. Now, if you will see here this definition of x, this definition of x involves both r and theta. X is depending on both r as well as theta. So it is function of two variables. So we will not be writing it like this, dx by dr or dx by d theta, because these are the notations for ordinary derivatives and these are used if x is function of only r. But this is not the case here because x is not the function of only r, x is function of both r and theta. And similarly here we can see that y is function of two variables r and theta. So we are finding their partial derivatives del y by del r and del y by del theta. So this is about notation. Now the next thing, that how we find out these partial derivatives. So when we are evaluating the partial derivative, say this first one, partial derivative of x with respect to r, all rules will be used. But the thing which we have to keep in our mind is that since we are differentiating partially with respect to r, so this theta will be treated as constant. So if I write down here, this will simplify. Before simplifying, let us write down the partial derivatives here. Del x by del r. Let us go to the definition of x, which is r cos theta. Let us differentiate x partially with respect to r, taking theta as constant, treating theta as constant. So cos theta will be treated as a constant and derivative of r will be 1. So it will be cos theta. Now del x by del theta. Now when we are differentiating x partially with respect to theta, now r will be treated as a constant. So this r will be as it is and the derivative of this cos theta will be minus sine theta. So what will be the result? Minus r sine theta. Now del y by del r, for this we have to go with the definition of y. Del y by del r, sine theta will be treated as constant. We will be differentiating r, so it will be sine theta because the derivative of r with respect to r will be 1. Del y by del theta, r will be as it is, sine theta will be differentiated and the result will be r cos theta. And when you will find it, it will simplify to r. We have used here the trigonometric identity that sine square theta plus cos square theta is equal to 1. So we have Jacobian as r. Now this one more thing is here. We can easily find out what is w by putting here x as r cos theta, y as r sine theta. We have evaluated Jacobian right now, that Jacobian is r. When we are considering these change of variable, we are changing the variable in this way that we are considering x as r cos theta and y as r sine theta. The one more thing which we need is the limit. And since now we have converted everything in terms of r and theta, so what we need the limits of r and theta. If you will see this integral, on the left hand side we have dx dy. So here on these integrals, we need the limits of x and y. And if you will see this double integral, which is in terms of u and v, here we are integrating with respect to u and v. So what we need here on these integrals, we need the limits of u and v. If you will see this third equation, in third equation, these limits 0 to infinity, 0 to infinity, these are the limits of x and y. But as we are changing to r and theta, so what we need to find, we need to find out the limits of r and theta. And how we will be finding those limits? For finding those limits, we need the region of integration, that over which region, over which two-dimensional region we are evaluating this double integral. How we will be getting that region? From these limits, we will be finding the region of integration. Here the limits of x are from 0 to infinity and the limits of y are from 0 to infinity. If you will see here, what we are saying that the limits of x are from 0 to infinity, means x is positive, and the limits of y are from 0 to infinity. So if I talk about the region of integration, that region of integration will be this first quadrant where both x and y are positive. This first quadrant is our region of integration. This complete will be our region of integration. Now from this region of integration, which is the first quadrant, positive quadrant, we have to find out the limits of r and theta. We have discussed in this figure what is the significance of r and theta. So what we will be doing to find out the limits of r and theta, we will be considering all radial strips, all possible radial strips in this region. You can see here in this region, which is the positive quadrant, this is the first radial strip. And if I talk about theta for this radial strip, what is theta for this radial strip? It is 0 because its inclination with positive direction of x-axis is 0. And if I talk about r, since x is from 0 to infinity, so r is starting from here, here r is 0. And since we can go up to infinity, so r will be varying from 0 to infinity. And for this particular red color strip, theta is constant and that theta is 0. Now, if I consider the another radial strips in this region, they will be like this, this. We have infinite number of radial strips in this region of integration, which is the positive quadrant of our two-dimensional plane. And the last radial strip will be this one, which is the positive direction of y-axis, this one. For all these radial strips, theta is constant. For this radial strip, theta will be this one. For this radial strip, theta will be this one. And this will be the last radial strip in this region of integration. So if we talk about the limits of r and theta, r will vary from 0 to infinity because these radial strips will go up to infinity. And if I talk about theta, then we can see from this figure that here for this one, which is the positive direction of x-axis, theta is 0. And this is the last radial strip in this region of integration. And for this radial strip, what is theta? Theta is pi by 2. So theta will vary from 0 to pi by 2. Now we have Jacobian, we have new limits, we have limits of r and theta. So let us rewrite this equation 3. So what we get, we are considering this product in third equation. It will be 4. We were having 4. The limits order of integration is here in polar coordinate system is dr, d theta. Order of integration means on inner integral, if you're saying that order of integration is dr, d theta, it means on this innermost integral, we will be having the limits of r, which we have just discussed, that the limits of r will be from 0 to infinity. And on this outer integral, we will be having the limits of theta, which we have discussed right now with the help of this figure, that for the positive quadrant, theta will vary from 0 to pi by 2. So these are the limits of theta. What is our integrand? E raised to power minus x square plus y square. When we'll put here x as r cos theta and y as r sin theta, x square plus y square will simplify to r square. So it will become e raised to power minus r square. E raised to power minus r square, and x raised to power 2m minus 1, it will become x is r cos theta, 2m minus 1. Y is r sin theta, 2n minus 1, r sin theta raised to power 2n minus 1. And if I then we will be having Jacobian. Jacobian is here r, and our order of integration is dr d theta. So we have changed our third equation into polar coordinates by using x as r cos theta and y as r sin theta. As our order of integration is dr d theta, so firstly it will be integrated with respect to r, and theta will be treated as a constant. So let us separate the terms which involves r and the terms which involve theta. 4, the limits of theta are from 0 to pi by 2. Limits of r are from 0 to infinity. And if I collect the terms of r, we have r in this e raised to power minus r square, and then r is present here. R raised to power, it will simplify to 2. 2 is common, m plus 2m plus 2n, and minus 1. This is our dr, this one. And we are left with cos theta raised to power 2m minus 1, sin theta raised to power 2n minus 1, and now we have d theta. We have already considered here dr. Now see this integral very carefully, this one. This integrand e raised to power minus r square, r raised to power 2 m plus n minus 1 dr. See this integral and go with your equation 1 and 2. You will feel that there is something which is similar in these equation 1, 2 and 3. Here we have e raised to power minus x square. Here we have x and 2m minus 1. And here we have m. And if you will see this equation, which we have just, this one, e raised to power minus r square. In equation 1, we were having e raised to power minus x square. So at the place of x, we have here r. In equation 1, we were having x raised to power 2m minus 1. But here at the place of m, what we have? We have m plus n. And in second equation, the variable is x. We are integrating with respect to x. Here we are integrating with respect to r. So if you compare this integral with first and second equation, we can write down this integral. Since we have here m plus n, we can write this integral as gamma of m plus n. So we will be writing that in the next step. And be very careful. In second and first equation, we have 2 also. This 2. So 1, 2 will be used here. Here we have 4. So we will be using 1, 2. So we will be left with only 2. Theta will be from 0 to pi by 2. and this 2 and this integrand, it will become gamma of m plus n, and we will be having this cos theta raised to power 2m minus 1 sin theta raised to power 2n minus 1 d theta. Now we are left only with one variable, theta. This gamma of m plus n is constant. So let us simplify it further. We get gamma of m, gamma of n. We can take this gamma of m plus n, since it will be constant, outside this gamma of m plus n. We are left with this integral. Limits are from 0 to pi by 2. And the integrand is cos theta 2m minus 1 sin theta 2n minus 1 d theta. Let us solve this integral which is present on the right hand side. This will imply gamma of m, gamma of n, 2 gamma of m plus n. Let us rewrite this. We can write it as cos square theta raised to power m. We can write down sin square theta raised to power n. This is divided by cos theta sin theta d theta. Let us take this gamma of m plus n on left hand side, because it will be in the same form which we have to prove. We have here 2. The limits are from 0 to pi by 2. We have sin square theta raised to power n. We can write this cos square theta as 1 minus sin square theta is raised to power m. This is divided by cos theta sin theta d theta. This implies gamma of m, gamma of n is divided by gamma of m plus n. For this right hand side, let us consider the substitution. Let sin square theta is t. With this substitution, let us find out the relation between dt and d theta. We will get 2 sin theta cos theta. This will be dt by d theta. And what will be the new limits? If theta is 0, t will be 0. If theta is pi by 2, sin pi by 2 is 1. So t will be 1. So let us convert the right hand side in terms of t with this substitution. It will reduce to, we have 2 here. The new limits are 0 and 1. Sin square theta is t, so it will be t raised to power m. 1 minus sin square theta, 1 minus t raised to power n. Then here we have d theta is dt upon 2 sin theta cos theta. So when we will be putting here d theta, as dt upon 2 sine theta cos theta, it will become 2 sine square theta cos square theta. And when we will be converting it in t, it will become 2 sine square theta is t, cos square theta 1 minus sine square theta, it will be 1 minus t, and this is dt. Let us simplify it further. Gamma of m on the left hand side, gamma of n is divided by gamma of m plus n. The limits, see, we are getting the same limits which we have in the definition of beta function. T raised to power m minus 1, 1 minus t raised to power n minus 1 dt. This will give us gamma of m, gamma of n, gamma of m plus n as this right hand side in the above equation is the definition of beta function. So it is beta of mn. And in this way, we have proved and we have established the relation between beta and gamma function. The another property of beta and gamma function is, we will not be going to prove it complete. We'll be just discussing that how we can prove this result. This integral sine x raised to power p cos x raised to power q dx, this is equal to gamma of p plus 1 by 2, gamma of q plus 1 by 2 is divided by 2 times gamma of p plus q plus 2 by 2. How we can prove this property? The proof is very much similar to the previous one. If I consider the left-hand side is this one, this integral from 0 to pi by 2 sine x raised to power p cos x raised to power q dx. What we will be doing here, we can write this as, we will be writing it in terms of sine square theta cos square theta, and then we will be doing it the same manner as we have solved this integral which was involving sine theta and cos theta. So let us write it in this way. This cos square x q by 2 dx. Use the same substitution. Let the sine square x as t. This cos square x will become 1 minus sine square x, 1 minus t. Find out the relation between dx and dt. The new limits will be from 0 to 1. And once you will be using the substitution, the limits will become the same which we have in the definition of beta function. Try to write it, the integrand, in terms of some powers of t and some powers of 1 minus t. And just identify those powers. What is the power of t and what is the power of 1 minus t? Because that will tell you that what is m and n, beta of mn. And once you have those m and n, use the relation which we have between beta and gamma function, this relation which we have established right now. Because once we have this one, m and n, then by using this relation, we will be able to prove this result. See the result which we have to prove on the right hand side, it involves the gamma function. With this substitution, it will be converted to beta function. You will be getting beta of some m and n that you have to identify that what is m and what is n. And once we have that beta, with the help of result which we have established right now, the relation between beta and gamma function, you will be converting it from beta to gamma. And in this way, you will be able to prove this result. So you can do it in this way. By proceeding in this way, you can complete this proof. We have one more property which we have discussed in our previous video, that gamma of 1 by 2 is under root pi. So we know here this result will be used. We know that beta of mn is gamma m, gamma n, gamma of m plus n. Consider m and n both has 1 by 2. This implies this right hand side will become gamma of 1 by 2, gamma of 1 by 2. So it will be gamma of 1 by 2 whole square, and this denominator will become gamma of m plus n, gamma of 1 by 2 plus 1 by 2, gamma of 1. And this is beta of 1 by 2, 1 by 2. We know that gamma of 1 is 1. So this implies that gamma of 1 by 2 will be actually the square root of what? What is on the right hand side? This denominator becomes 1. On the right hand side, we have beta of 1 by 2, beta of 1 by 2. So what we have to do for finding this gamma of 1 by 2, we have to evaluate this beta of 1 by 2, 1 by 2. So for evaluating this beta of 1 by 2, 1 by 2, what we'll be doing? We will be using the formula, we will be using the definition which we have for beta function. So do it on your own, find out this one by using this definition which we have for the beta function. It is from integral within the limit 0 to 1. Then we have x raised to power m minus 1, 1 by 2 minus 1. It will be this. 1 minus x, n minus 1, which will be minus 1 by 2 dx. So evaluate this integral, and after evaluating this integral, prove this result. So in this way, you can continue this one, and you can prove that the gamma of 1 by 2 will be square root pi, means this integral should come as pi. So in this way, you can prove this property. So that's all. We will be discussing some more topics in our next video.